So in the first part of Unit 2, we worked with exponential functions, and then we took a little side quest into function composition and inverse functions. And the reason we had to do that little side quest is because when we start working with the second type of equation or function in this unit, we needed to know how it related to the other things in this unit. So all of this to say, if we're just thinking about operations in general, what's the inverse of addition? Subtraction. Yeah, don't overthink it. The inverse of addition is subtraction. Great. The inverse of multiplication is what? Division. So if we had a division problem and we wanted to solve for x, we would multiply or vice versa. What about if you're cubing something? What's the inverse? Cube root. Okay, so we have all of these abilities to undo a function type. But what if we had the type of function we had at the beginning of this unit? What if we had an exponential function, 3 to the x equals 7? How do you solve for x? That's a great question. I'm so glad you all asked it. This is going to be where our logarithmic expressions and logarithmic equations come into play, which is the second type of function that we're going to learn about in this unit. In Algebra 2, you did learn about logarithms, but I think it's towards the end of the year when everybody checks out. So I'm going to assume that we don't know very much about a logarithm when I'm teaching you about them. Okay? Sound good? We are going to work on first just understanding what a logarithmic function is, so then we can use it to solve exponentials and use exponentials to solve logarithms and back and forth since they are inverses of each other. But a big idea here is that just as you can write the decimal 0.5 as a fraction 1/2, they're the same number written in different forms. You can also write equations in exponential and or logarithmic form, meaning they're going to be equivalent like 1/2 and 0.5. They're just going to be written in different forms like decimal and fraction. One of the forms is going to be called exponential. One of the forms is going to be called logarithmic. Now, how do we go back and forth between these forms? The same way you would know how to change from a decimal to a fraction. Great question. What's going to happen here is we'll have an exponential. So there's a base, a power, and a number that it's equal to. And then we'll have the logarithmic form. What do you notice about this form of a logarithm? What do you notice has appeared in it? The word log. Yes, that's our indication that we are working with a logarithmic function. Do you see that it uses the same letters as exponential? They're just like in a different order, right? Let me help you find out where they go. So the first order of business is we have our base, b. Do you notice that the base is the base where we would put the base in an exponential? And in a logarithm, it's like a subscript. That's going to be the base of a logarithm. That's where we indicate what the base we're working in is. Then if you notice the letters we have left, we have the letter A that originally was next to the B. It was the power, what we were raising it to. And then if you look in the logarithmic form, it's now across the equal sign, and it's the evaluated number. It's what we get when we take the logarithm. And then we have in exponential form the number that it's equal to, like what you just did on the GIM kit. 3 to the third power equals 27. This is the equals to number. When we're doing a logarithm, that number actually becomes the number we're plugging into the logarithm instead of what we're getting out of the logarithm. So we have created what's called, for me, a log loop. So if you'll notice, the base never changes, but the A is going to go away from the base or towards the base if we're switching back and forth. And the C is going to go towards the base or away from the base if we're switching from one form to another. So that's the main idea of today, is that the base never changes. The only time we ever change a base is if we're doing topic 2.4, and we're raising a power to a power. That's the only way we'd change a base. Otherwise, bases never change. And then we're going to do the log loop. We're going to loop the A and C around to different positions to rewrite these as exponential or logarithmic form. Now, there's two important notes for us when it comes to logarithms and the notation that we use. We have a type of logarithm that's used so often, it's called a common logarithm, and it is so common that we have made a shorthand for it. So kind of like square root, you don't put the 2 on the outside of the square root because it's so common. A common logarithm is a base 10, and if you have a base 10 logarithm, you're just going to write it as log. It is written without the base. So if you see log with no base showing, we mean log base 10. That's called a common logarithm. Additionally, there's another super common logarithm. It's not called a common logarithm, but it's used super often, and it's called a natural logarithm. A natural logarithm uses the natural number e as the base. But you won't really see log base e written out because that looks kind of weird to me. This is actually a natural logarithm. So we switch the notation to say ln. That is not in, that is ln. In fact, I write my natural logs in cursive so that you don't think it's an ln. So that might be helpful for you. Okay, so we have two separate types of special cases when it comes to logarithms. Your common logarithm is base 10. Your natural logarithm is base e. Hang on to that information, and we're going to log loop some of these things. Our first two examples is just converting back and forth from exponential to logarithm or vice versa. I'm only going to color code one of them, and then we're just going to rock it out from there. But if we have 3 squared equal to 9, which is a true mathematical statement, 3 squared is 9, and we wanted to write it in in logarithmic form, we're going to take the base. What's the base here? 3, and we're going to write the base as the base part of the logarithm. So it's the subscript after log. Then I'm going to take the exponent and the number it has been evaluated to, and I'm going to loop them around, which means that 9, which was far away from the base a second ago, now is the number I'm plugging into this logarithm. And the number I had originally raised that exponential to is what I get out of the logarithm. It's reverse. It's inverse. Your outputs become inputs. You're switching the x's and y's. Does that make sense? I'm not going to color code much more on this, but we're gonna keep rocking with these. For number b, what is the base? 10. So if I have log base 10, then if I'm doing the inverse function, which exponentials and logarithms are inverse, I'm just going to switch the x and y. So I should write this as log base 10 of y equal to x. I've switched the location of the x and y. It's a log loop. Inputs become outputs. But log base 10, we will never write it like that. How did I say you could write log with a base of 10? Just log. So this is going to be log of y equal to x. You don't need those parentheses. My g's and my y's just look very similar, so I want to make sure I see a difference in them. So that's my handwriting problem. But log of y equal to x is log base 10 of y equal to x. Okay, what about c? What is the base of expression c? R. So we're going to write log base r of what? W equal to t. You're looping them around, so the output w becomes the input of the logarithm. Your input t becomes the output of the logarithm. Now what about d? What is the base here? E. Very good. So the base, remember, is the thing with the power. So the thing that has a power right now is e. So my base is e, and I'm going to switch what was the output and the input. The output was y, which means that becomes the input. And my input was 3x, so that becomes the output. Log base e of y equal to 3x. But you will never see it written like that. What did we say log base e could be written as? ln. So this is the natural log of y equal to 3x. Again, I write that in cursive so that my brain doesn't accidentally think that's in. It's ln, natural log. Do we see the log loop and how it works going from exponential to logarithm? What if we go the opposite direction? This time, we have it in logarithmic form, and we want to change it back into exponential form. So for this first problem right here, what is the base? 7. So that means I'm going to make a really big 7, because 7 is now my base. It's the big number that needs a power. In the logarithm, we are equal to 2 when we plug in x. So that means when we switch this back, what is going to be the input? Is the input 2 or is the input x? 2, and it's going to be equal to x. You're just looping it back the opposite way. If you can identify the base and then move some things around using inverse ideas, then we're great. For number B, what's the base? Which means that the base is 3. If I have an output of x and an input of y when it's a logarithm, when it's an exponential, the input is y and the output is x. That's a big lie. I said that all the way backwards. Beep, 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 beep. I'm so sorry. Okay, number C. What's the base? 10. Yeah, if it's not showing, remember that's a common logarithm, so that's base 10. This should be 10 raised to what power? 2 equal to y. Very good. We've just written it in its inverse form. Now what about D? What's the base there? E. Because its natural log is log with a base of e. E to what power? 4 is equal to c. So you're switching the inputs and outputs, which is what we did when we did inverse functions. Do we feel okay about that? Great. So why do we do this? I'm so glad you asked. Why do we even have this conversion? To do problems like this on the back. I'm now going to ask you not to only be able to evaluate power families, but I'm going to ask you to evaluate logarithms without a calculator. Now, we don't think very well in terms of logarithms, but you guys did really well on that Blue-Kit when we were thinking in terms of power families. So what's really helpful when we're evaluating logarithmic expressions, especially without the use of a calculator, is changing it into exponential form and thinking about those power families and your exponent rules. Meaning, I'm going to do the following. We want to evaluate log base 2 of 8. So we're trying to figure out what log base 2 of 8 is equal to. In mathematics, when we don't know what something is, we don't put a question mark there. What do we usually put when we don't know what a value is? X. So instead of putting a question mark, we're just going to put an X here. And we're trying to figure out what this is equal to. Good thing we have our log loop, though. If I loop this back into exponential form, which we are much better at thinking in, this is going to be 2 to some power equal to 8. And guys, y'all just did that whole Blue-Kit about the power families. 2 to what power is equal to 8? 3. So if I rewrote 8 as 2 to the third, you see that x has to be what number? 3. So log base 2 of 8 is equal to 3. So if we think about it in its reverse form, in its inverse form, in the exponential, we actually can solve these questions a lot easier. Can we do this one for B? What's the base? 5. We want to raise 5 to some power to make it equal to 25. What do I have to raise 5 to make it equal to 25? 2, because 25 is 5 squared, yeah? So log base 5 of 25 is 2. Notice how I'm saying that? I'm going to ask you to pronounce these logarithms correctly. Log base 5 of 25. Log base 5 of 25 is 2, since 5 squared is 25. Okay, what about C? What's the base? 2. I'm going to raise 2 to some power and hope that is equal to 32. Uh-huh.
5, right? No. 6. Wait, no. That was 5.
It was 5, yeah. So log base 2 of 32 is equal to 5. See why I made y'all do that over and over again for the last few class periods? I had a master plan. Okay, what about this one? What's the base? 10. Yeah, because it's a common logarithm that's base 10. We want 10 to some power to be equal to 100. 10 squared is equal to 100, so log of 100 is equal to 2. It's easier to evaluate these in exponential form than logarithmic form, but we're doing the same thing. Now, of course, it can get harder, but I've still got you. I'm here with you. Okay, what's the base here? 16. 16 is some power needs to be equal to 4. Ah, I'm so glad you remember that. Well, remember, if we're trying to make numbers smaller in power families, we need to use fraction exponents. Isn't the square root of 16 equal to 4? Which means that 16 to the 1/2 is equal to 4. So log base 16 of 4 is a half. Okay. What's the base here? 3. I need 3 raised to some power to be equal to 1. Whoa. No, that would be the cube root of 3, which is not 1.
Isn't it just 1?
No, because 3 to the first power is 3.
0.
0. Anything raised to the 0 power is 1, correct? So the logarithm base anything of 1 is always going to be equal to 0. Because 3 to the 0 is 1. Okay, what's the base here? 10. So we have 10 raised to some power equal to 10. So it's 1. Log of 10 is equal to 1. What if I make it challenging like this? What's the base? 6. 6 to some power is going to be equal to 1 over 36. Do you recognize that 36 is a part of the 6 power family? Yeah, it's 6 to what power?
1/6.
What? 6 squared, right, is 36. But now that 36, the 6 squared is in the denominator. How do I get it out of the denominator? No. Make it a negative. Remember, negative exponents go to the bottom. So if you want it out of the bottom, you make it negative. So log base 6 of 1/36 is negative 2. So it can get complicated with these power families, which is why I've been having you do this multiplication over and over and over again at the beginning of class, because I wanted us to be prepared to be able to do these logarithms. Now, you can evaluate these in a calculator, but you know part of this class has no calculator, so you do need to know how to do it by yourself. But let's say that you're asked to, on the calculator section of a test, evaluate log of 9. There's a very, very easy way to do this. Everybody look at their calculator for me. Do you straight up see a button on there that says log? Yeah, it's next to the 7. Press that button next to 7 and then type 9, close the parentheses and press enter. It's going to evaluate that common logarithm for you. We'll round to 4 decimals. Log of 9 is approximately equal to 0.9542. Yes? There's a whole button for that. Great. There is also an entire button for natural logarithm. I want to bring your attention to that. I don't ask a question about that. Do you see right under the log next to 4, there's an LN button? You can use the natural log button to evaluate natural logs on your calculator. Okay, what if I was asking you for log of 6,125? Again, you just press the log button, type 6125, close the parentheses, and then round to 4 decimals, which means you should get 3.7871. Cool? Great. But then we run into a problem. Look at these next 2 problems. What are the bases of these 2 problems? 2 and 7. The buttons I have on my calculator are only for what bases? 10 and natural log. E. So we have a problem. The buttons on my calculator only work for common logarithm and natural logarithms. These are not that. So you have to go looking through your calculator to help you out. On your calculator, you're going to press the math button. And you're going to scroll all the way down to option A, which says log base. Your calculators are now smart enough to be able to do logs with changes of bases. So if you open that up, it opens up something on your home screen that looks like this, where you have a space to type a number in here and a space to type a number in there. You can still evaluate logarithms using your calculator that aren't common logarithms or natural logarithms. But of course, don't just make that mean that you're not ever going to think about logarithms again, because you will be asked to do that without a calculator. Either way, if you do log base 2 of 10 in your calculator using the math and then log base, log base 2 of 10, when we use the log base format on the calculator, we should get approximately 3.3219. Do you agree? And then if we do log base 7 of 125, again, you have to use the log base function. We should get approximately 2.5208. Yes? Fabulous. Now, what's the point of all of this? Obviously, we can use logarithms to eventually solve exponentials. So if we were asked to solve a function, we would need inverse operations. So that's super helpful. But additionally, there is a really, really big application of logarithms in a lot of engineering and a lot of computer systems that we're going to start dipping our little toes into in this class. We end this unit with an actual lesson over these kinds of plots, but I'm going to get us started here today. If you just think about exponential data, so this is a big shift in what we're talking about. If we think about exponential data, like this example here, we have this exponential information, right? It goes up, boom, keeps going, keeps going, keeps going. What's really unfortunate about exponential graphs is that we lose a lot of information very quickly because you can't zoom in on the beginning and the end of an exponential. It goes off screen very quickly. So for example, these two graphs are going to show the population of English Americans in the current United States since 1620. Okay, it has grown exponentially. Population growth always grows exponentially. The estimated population is shown below for 1620 through 1820, where T represents the number of years after 1620. This graph on the left is a normal exponential plotting this data. If I were to ask you to look at this data and tell me how many English Americans were in the current United States in 1620, basically like how many pilgrims came over here, how many would you tell me based on this graph came over here? Zero. Does that make sense though? Does it make sense that 0 pilgrims came over here? We know they came. Yes? So we have a problem here. Our data is not really helpful in this format. So we run into a problem with exponential graphs, especially when you're using them in fields of engineering and computer science, when you need all of the information for yourself. So we can do what's called a logarithmic scale. I want you to highlight this word for yourself. A logarithmic scale. Oops, not in blue. I meant to do that in yellow. A logarithmic scale base 10 for our vertical axis. If you notice, our vertical axis changed from 1 million, 2 million, 3 million, 4 million, 5 million, 6 million, 7 million to powers of 10. My question for you is, just to make this make more sense to us, what is 10 to the first power? What's 10 to the second power? What's 10 to the third power? 1,000. Keep going. And then 1, 2, 3, 4, 5, 6. Okay, so now our scale is not even. We are not counting on a normal coordinate plane anymore. We are counting on what's called a log scale plane. But if I look at this log scale plane, this is the same data. Okay, I switched it from having a regular Cartesian plane to having a log scale. If I asked you the same question, how many pilgrims came over here, how would you estimate that? About 500. That makes more sense. That feels like a ship full of people. 500 people landed in, what's the place they landed? I don't do history. Plymouth? No. Yes. Massachusetts somewhere. Salem? No, that's right area, wrong city. But anyways, so what happens here is these logarithmic graphs actually make the data more legible for us as people who use the graph to do something with the information. So our goal today is to kind of start understanding these log scale graphs so that we can see exponential data in a logarithmic scale. They're going to go hand in hand. Okay? Let's just practice plotting some points. So on the next page, this really goes together. I have this graph here. It's the same graph as the page before. I've just made it bigger so we can use it. Okay? The population data of English Americans in the current United States for the years 1840, 1816, 1880 are given below. We're going to plot these 3 additional points on the same graph from before. So again, this is the same graph we had on the page before. I just made it bigger. And I also added more input values. If I'm trying to plot the population for the year 1840, I know that that is 220 years after 620. So that means I'm using this input data. Now, at the year 220, so 220 years after 1620, my population is 17 million. If I'm trying to put that on a log scale, I need to know how many zeros are included in that millions. I said 10 million, right? That's 10 to the 7th power is 10 million. So if we want 17 million, that means we need our coordinate point for this data to be just slightly above 10 million. So we're going to go from 220 all the way up to approximately above 10 million. Our next data point is 1860. That's 240 years after 1620. It says that our population at that time is 31 million. That's still within the 10 to the 7th power area, but it's going to keep going up. So at 240, I'm going to go up to a little bit higher than 17 million because 31 million is bigger. For the last one, for 1880, that's 260 years after 1620. And if my output there is 50 million, that's halfway between 10 to the 7th and 10 to the 8th. So if I add over here a 10 to the 8th, you can't see that, it got off screen. 10 to the 8th, that means I want my next dot, my green dot, to be halfway in between the 10 to the 7th and 10 to the 8th. So our population continues to grow, and even though that data is wildly different, because we're multiplying by a number here, we can see this linear pattern over our logarithmic scale, which makes it way easier for us as engineers in the future to get information from this data. Now here's some complaints I kind of assume it's happening because I also agree. That was really hard to plot because those lines, like there's no lines on this thing to help me find nice coordinates. So we can solve that problem by using what's called a semi-log plot. This right here is a semi-log plot or a semi-log graph. These are legitimately used in the future if you, depending on what you do with your life. So this is not made up math. This is like engineering, okay? This semi-log plot now provides me with lines that will allow me to have an easier time plotting more accurate points on the log scale graph. So let me just help you understand what's happening here. This big bold line is 1. Is it 0? It's labeled as what? There's no 0 on this graph. There's no x-axis, the way an x-axis typically works, because this is the number 1. If this is the number 10, and this is the number 1, what do each of these lines in between here represent? Let me rephrase. What is this? 2. What's the next one? 3. What's the next one? And I'm going to run out of space because I can't write that small. But do you see how this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? If this is 10 and this is 100, what's this line? 20. And then 30, and then 40, and 50, and 60, and 70, 80, 90, 100. This is 100, this is 1,000. What's this line? 200. Do you see how this works? Okay, this is a semi-log plot. It allows me to plot the points like we did up above, but like legitimately more accurately. So that's what we're going to practice right now is plotting these points. If the first thing I want to plot here is 1 comma 20, the input value is still 1, but the output value is 20. So I'm going to go to 1, and then one line above 10 is 20. So 1 comma 20 is right here. That's A, 1 comma 20. Plot and label. Number B asks me to plot 2 comma 300. So I know my input value is 2 and my output value is 300. So that's going to be just a few lines above 100. This is 100, this is 200, this is 300. So this line right here is 2 comma 300. My next coordinate I'm plotting is 3 comma 2. So I go to the input value of 3, and I want the output value of 2. If this is 1, that means this is 2. So my input value should be, boop, right there. That's C. Are we following? Okay, 4 comma 15. Input value of 4. Output value of 15. Ooh, how do I do that? In between 10 and 20. So if this is 10 and this is 20, 15 is obviously somewhere in between them. So this right here would be D. Same vibe for the last one. If we're trying to plot 5 comma 350, we know the input value is 5. Where would the output value be 350? This is 100. Just kidding, I pointed at the wrong thing. This is 100, 200, 300, 400. So in between 3 and 400, we want to put our little dot. So 1, 2, 3, 4. Boom. There's E. So my semi-log plot allows exponential data, eventually when we get to this lesson, to appear linear, which allows us to make better conclusions about all of the data because we're not missing the bottom or missing the top depending on how we zoom and print our graphs. These will keep coming back. After we learn a lot about logarithms, we're going to come back and do this again, and we'll learn a little bit more about semi-log plots, but these are like legitimate things in engineering. So much so, my dad was an engineer. He just retired. Good for him. And he gave me one of his textbooks that he got on the job. And let me see if I can find the log plot. Oh, turn this off.